Chapter 18-19 review. We are looking at comparing force, E-field, potential, and electrical potential energy. Those are the four big concepts between the two chapters that you need to keep straight. You're pretty familiar with force, you know it's F and measured in newtons. E-field, you've had gravitational fields, you kind of get it as the area around the charge is measured in newtons per coulomb or volts per meter. Potential is really new, that's our newest concept, and that's V, and it's measured in volts or joules per coulomb. And electrical potential energy is just like our good old friend energy, can be converted in any kind of energy, kinetic energy, or gravitational potential energy, or heat energy, or whatever we want it to be, and that's in joules, just like it always has been. So definitions are just sort of the concept behind each one. Force is push or pull. E field is the area where the force is felt. Potential is energy per charge, right? So there's nothing there until you put the charge there, but originally it's just energy per charge. And then EPE is total energy. So when I put a charge there, I get the total energy. There's no energy here until I put a charge at that potential point. The equations, F equals KQQ over R squared. That's Coulomb's law. We know that is inverse square. Should make sense. There are three equations for E field, and you need to keep them straight. So E equals F over Q is straight from the definition. You can use that anytime you want. There's no issues there. But this one right here, oops, that's not what I wanted. This one right here, let's try again. This one right here is for point charges only. So we only use that one for point charges. So let's put a little note there, come over here, make it smaller, maybe about 22. All right, so this is only for point charges. Don't use it any other time, only for point charges. Now this one right here, that one we only use for parallel plates. So this one right here is only for parallel plates. So don't use it any other time. Only for parallel plates. Okay. And then potential is got three equations, sort of. Well, V is the absolute potential, right? This is again for a point charge, but that's all you're going to have it for. Is V equals KQ over R. So just like this one, that is only for point charges as well, right? That's the only time you can use that. You can't use it any other time. This is difference in potential. So this is really what we call voltage. And so that's what provides work. So you can't have any work unless you change your potential. And so the negative W is, delta V is negative W over Q because of the way the charges work, which we'll get into more into the review. But the idea is, right, if I have a negative Q, this becomes a positive, and if I have a positive Q, it becomes a negative. But usually using concepts is easier than actually using the math formula. But that is the right math formula if you want to use it. And then we have UE. Now, technically, this UE right here is a delta UE, so it's the change of potential energy is equal to delta V times Q, because you could have a UE without a delta V, right? But then you're just back to this. And then you have UE equals KQQ over R because it's just V times Q, so that's just if you take your KQQ over R and you multiply it times Q, you get your total energy because that was energy per charge. Then we know that force and E field, of course, are vectors. You have to add them like vectors. And potential and electrical potential energy are scalars. You have to add them positive, negative, but this direction doesn't really matter. But they can be positive or negative. So that's important. And so for Fn, the direction is determined by both charges. So positive and positive are going to repel. Positive and negative are going to attract. So you figure out if it's going to go left, right, up, down based on that. The direction is defined by a positive test charge for the E field, right? So the E field is always defined that way. It's just a definition. So you just have to know that a positive charge, the E field is going to point away from a positive charge, and E field is going to point towards a negative charge. Potential can just be positive or negative, and negative is at a lower potential than positive. So it is like being on a number line. And UE, again, can be positive or negative, and again, negative is at a lower energy level as we define it. So now let's say we want to figure out, we're trying to understand the difference between F, E, V, and UE, right? So let's say I put a negative charge right here, and I want to know the force on that negative charge. So the first thing I'm going to do is I am going to draw the direction of all of my forces. So I'm going to make this an arrow, and let's make it maybe, I don't know, green. And so I look at F1, and if this is a negative charge, it's going to be attracted. So F1 is going to pull it like that, right? And F3 is going to pull it like that, and F2 is going to push it away, right? So then I'd add up the vectors. I'd have to add up the components. So I could come over here and I could make components right here, and I could figure out the components here, and then I could figure out the components here, and then I would subtract those two x's, subtract the two y's, and whatever's left, do Pythagorean theorem, and be able to figure out the net force on this object at a certain angle. So you would actually know angle, no positives or negatives there. Now, on the other hand, what if I came over here? Well, this one, I have to imagine there's a positive charge there. So it's going to be the opposite of this, right? But I can still draw my arrows. So let's draw arrows again, and let's make it here. And we'll go back. Let's make it blue this time for the E field. So since it's a positive charge, I want it to be this. Let's try again. This, there. All right, so it's positive, so I want it, it's going to point away this time, and it's going to point away from number 3, and it's going to point towards number 2. And again, I would add up the components and be able to figure out what the E field is. If this had been a positive charge, I could simply just divide it by Q. I could still just divide it by Q, it's just the direction is going to be opposite this one because everything's pointing the other way. So that's E fields and F. A little pain in the neck because you got to do some vectors. Now, if we're doing this one, potential, I just have to add them up. It's just a scalar quantity. So I don't even draw any arrows. I just go, oh, this is just going to be KQ1 over R minus, that's not minus, minus KQ2 over R, and then plus KQ3 over R. So that'll give me my total potential at that point. It's just a scalar. I don't care. I have to know the distances, right? This has to be the distance for this one and the distance for that one. No squares. Really, really simple. For UE, a little more complicated. We talked a little bit about it today. So if I bring in the positive charge here and nothing else is here, it takes no energy to do that. But it's going to create a potential here when I bring in number 2. So I'm going to bring in 1, then 2, then 3. So I bring in 1, no energy, no KQ. But now I'm bringing in 2. So remember, UE is KQQ over R. So I need the KQ over R for this guy. So I'm going to start off with KQ1 over R12, right? And then I'm going to multiply that by the Q I bring in, which is Q2. And then I'm going to add that to the potential for the other ones, right? And so this energy would be negative, right? So I leave with the negatives, the positive negatives have to stay there. And so now I'm going to do it for number 3, but now I've got both of these, so it's going to be KQ1 over R13, right? And then minus KQ2 over R23, because there's 2 of them, right? And that's that distance, and that's this distance, right? And then I'm going to multiply it times Q3. And I'm done. That's it. So I'm just doing KQQ over R plus KQQ over R. Right? And then my Q I just put on the outside. I think conceptually that makes sense. It makes sense to me. Hopefully that makes sense to you. Capacitors, the things you need to know about capacitors is that Q is equal to CV. I always do it this way because I always mess it up otherwise if I do C equals Q over V. Capacitance is equal to kappa epsilon naught A over D. Remember, A is the area of the plates. D is the distance of separation. Epsilon naught is the permittivity, the vacuum permittivity, I guess Katie explained to me today. I've always called it permittivity of free space, but it's a constant. Kappa is based on the material, right, that's inside of it. So this one changes depending on what it is. Kappa is always the ratio. This is important. This part people always forget that, what the heck is this? And we didn't talk about it that much. So make sure you realize that kappa is this ratio between E naught and E. And I want my E field strength to go down, so that means that I get kappa to be big, right? So if E goes down, right, kappa goes up and I have more storage capacity because that means it's not going to push the Qs out. And we did talk about that, but only like once. So if you add a dielectric, it decreases the E field and increases the capacitance. So that's a good thing. And then you see the energy of capacitor is 1/2 CV squared. You can also, there's another one if you look on your equation sheet, but this is the one I always remember, but the other one's there. And so you can replace capacitance, I think, with Q over V. Yeah, so if we replace that with Q over V, what will we get? Make sure I do this right. 1/2, if it's Q over V, it would be QV, right? So it would be Q, doesn't matter which way you go, Q, V. So I just plugged it in. So it doesn't really matter, but this is the one I remember the most because it's kind of like 1/2 mv squared, so it's easy to remember. Polarization, this is just a concept. Make sure you remember it. This is all from AP1. So if you bring a charged object next to a neutral object, you will polarize it so it separated the positives and negatives. So now the negative and the positive stick. So it causes neutral objects to attract to charged objects and causes ground link. And it causes charging only if you ground it. So remember, we played with that induction plate, and so we bring something in that's charged, but there's no charges moving between the two because it's just near it. It just polarizes it. If you ground it, like touch it or something like that, now there's a path for the electron to either to go in or out, depending on, in this case, the negatives are getting pushed out because it's a negative rod. If it was a positive, then the positives would be repelled and it would attract the negatives. So you end up with opposite charges, so these will actually attract if you do induce polarization charging. So conservation of E field. The E field and outside work can cause an increase or decrease in the potential energy and the kinetic energy. So here, look, this is just our energy equation that we've always seen, right? So we have UE initial, oh wow, we used an I, plus KE initial plus work is equal to UEF plus KEF. So it's just like we've done before. Normally what happens is the change in UE becomes delta VQ, and you just set that equal to 1/2 MVF minus V naught squared, right? Because this is the change in energy is equal to the change in kinetic energy, because we basically make electrons and protons fly through a potential difference, and we get them to go a certain speed, right? Remember, work is equal to negative delta UE. So this is the work done, and important, by the field. By the field and charge of UE on by the field. This should be on by the field and change of UE of charged particle. Well, it's by the field and on. Okay, so maybe we'll erase that. I think I had it right to begin with. Go back. So this is the work done by the field and change of UE of the charge particle. So that's what that's saying. But they're opposite, right? So the idea, the concept here is if I move the positive, if I put this here and it goes this way, the potential is going down. This is a so it would be a negative change in voltage. Or in potential. It's like it's going down, right? And so it's going to go faster. So you end up with 1/2 MV squared. The big concept is to think, is it gaining energy? Is it losing energy as potential? Or is it gaining or losing energy as kinetic? So if it's gaining kinetic energy, it must be losing potential energy. And if it's gaining, so here it's gaining kinetic energy, losing potential energy. If it goes the other way, it's gaining potential energy and losing kinetic energy. And if it was negative, it would be the other way around, right? If I put a negative charge here, it's going to gain potential energy and lose kinetic, and if it goes this way, it's going to gain kinetic energy. So just think which way it wants to go. If it's going to go faster, then it's gaining kinetic and losing potential. And if it's positive work, if it gains kinetic energy, right? I think that makes sense. To me, that makes more sense than all these silly negatives and positives. And anyways, they work, but I get more confused personally that way. Miscellaneous things to remember. So don't forget, the charge of an electron is negative 1.6 times 10 to the negative 19th coulombs. Of course, you could use that charge for a proton, but then it'd be positive. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, because remember that that's the energy it takes to move 1 electron through 1 potential difference. So Q times V, right? This is Q E times 1 volt, because that's the definition of it, right? And so that's why it's 1.6 10 to the negative 19th. It's not a coincidence. Micro equals 10 to the negative 6. I've seen people take my test and totally forget that the micro means 10 to the negative 6, and they miss all the points for that. And we've talked about this before, but just remember that equal potential is perpendicular to the E field. So if I go along, so if my E field, let's see, this one's going this way. So my E field is pointing like this, right? So these lines that are perpendicular are equal potential lines. So if I move a charge along those lines, no work is done. It takes absolutely no work. It's like doing centripetal force, right? It's perpendicular, so therefore it doesn't do anything. And here, same thing, right? My equal potential lines, if I can draw a circle, okay, that's supposed to be a perfect circle. That's perpendicular to these E field lines, right? Which that looks like it's positive. So since it's positive, the E field is pointing away, but those are perpendicular, so there'd be no work if you went around in a circle like that. And then that's just a dipole if there's two. All right, so hopefully that helps. Good luck on the test on Tuesday.